Okay, second session, and I'm going to break this up as lectures 1 and 2. Okay, so the first half will always be the first. Yeah, I'll count it as different lectures. Okay, just helps me keep track as like a regular quarter. Okay, so let's begin. Diodes. So, as I stated earlier, we studied resistors, capacitors, and inductors, linear devices, RLC. Resistors, inductors, and capacitors. Passive components, linear devices, and we learned circuit analysis. Now, circuit analysis methods are mostly analytical. Okay, analytical. And what it means is that the solution for a system that comprises of these three components is pretty much fixed. For instance, you have Ohm's law, V equals IR. Ohm's law is pretty much fixed. Now, of course, there are temperature limitations. Ohm's law is valid for a wide range of temperatures, but as with nature in real life, if it gets really, really hot or really, really cold, then most laws are no longer valid. So Ohm's law is valid for a wide range of temperatures and conditions. It's not valid when it gets too hot or too cold. Anyway, the point is that analytical means the solution is fixed. It's predictable. And repeatable. Okay. But now we are going to study semiconductor devices, which is basically diodes, transistors, or known as BJTs, and FETs, field effect transistors. These are non-linear devices, and the solutions for these systems are numerical. Meaning they are not fixed, they are approximations. They are approximations. So we have to make assumptions. We make certain assumptions, and then we can have or derive an approximate solution. Okay, approximate solution. So they are approximations. Now, as an example, take 10 seconds and think of one word that can describe you. You don't have to share that with me or with anyone, but take 10 seconds to think about this and think of one word that can describe you as a person. Okay, 10 seconds. How many of you were able to think of one word to describe yourselves? Okay, does it describe you entirely? No, but it does describe you. So it is true, but it's an approximation. What if I give you two words? Right? Two words will describe you much better than one word can, but it is still an approximation. If I give you one sentence up to 10 words, that would describe you even better. So all of those are models that describe you or that describe you as a person, but all of them are approximations. The point being that systems which use diodes, transistors, FETs, nonlinear models like these, we use a variety of analytical models to describe the system. Okay. Electrical engineering students, when they study this, similar to 201, when they study this, it is for an entire academic year. Okay, 201 is basically one entire academic year of a EE student. They also learn about circuit analysis, but they go scuba diving, whereas the non-EE major, the snorkeling. You're learning, we're skimming the surface and learning about circuit analysis from the surface. Same thing with 321. 321, we're going to skim the surface. So we are not going to go too in deep or too in depth into all the various models because it would take more than one academic year to actually get to it. Okay. What we're going to learn is some of the basics of how these devices are created, and then what you can do with these devices, meaning the circuits that you can build using these devices. So we'll learn about diodes, transistors, operational amplifiers, or op-amps for short, and then we'll get into the digital stuff, digital logic systems and computers. Okay, so at the end of this course, you will see a brief introduction, obviously, to computers and what it can actually do. And I always like to bring up the Arduino. The Arduino is a microcontroller board, is very, very popular. Actually, I just finished a high school project where we were showing them about Arduino and what we can do with it. So this was a quick and easy build of a temperature and humidity sensor. Again, so this is a sensor right here. And the sensor is basically based on resistors and capacitors. So the resistive sensor and a capacitive sensor in here. You connect it to this microcontroller board, and it can display the temperature and the humidity, which is what you see in the slide. So this was when I was teaching virtually. We were teaching EE251. We built a voltmeter using this Arduino, and then we also built a temperature and a humidity sensor using this Arduino. Okay, so these are some, this is something that would be expected of you as a non-EE major. How to take off-the-shelf components and build a system. Does that make sense? Right? So you don't necessarily want to know how. Obviously, it would be great if you want to learn how a device works, but it's not necessary for you to know, because what you need to know is how you can use this to build a system, build a circuit using a discrete component. So let's go back to chapter 1. Okay, Star Wars fans here. I'm not that big a Star Wars fan, but I like this meme. Hit the ground running we shall. So EE201, the concepts that you will need: Ohm's law, Kirchhoff's laws, and well, equivalent circuits. What is equivalent circuits? Norton and Thevenin equivalent circuit. Because many times, many of these analytical models will require you to quickly recognize what the Thevenin or Norton equivalent would be of a larger system. Not too much, and I will explain every time we go along. I recognize and understand the fact that for many students, it's been a while since you took 201, and so this might be a little bit of a blur. But when the time comes, I will make sure that I will explain. Okay, little bit of a brief history about electronics. Before we had solid state devices, we had vacuum tubes. Vacuum tubes come in all sorts of shapes and sizes. The first vacuum tube, probably about this big, small glass tube, which is completely sealed, and you had 2 electrodes inside it. There was the anode, which is right here, and there was the cathode, which is right here. Okay, 2 electrodes inside it. There was a heater right below the cathode, like a light bulb, like an electrical light bulb, filament light bulb. So that heater would be connected to a energy supply or source, heat up, and it would heat up the cathode because it's in close proximity to such a high temperature that the cathode would start emitting electrons. Okay, it would start emitting electrons. These electrons would float on the surface of the cathode. Now, this is just a basic explanation, but these electrons would float on the surface of the cathode. If we connect the anode and the cathode to an external power supply, positive, negative, an external power supply, what would happen? Electrons have what kind of charge? Electrons have negative charge. Anode is connected to the positive end of the supply. Opposite charges attract, same charges repel. So if you have a positive and a negative connected here, the electrons are attracted to the anode, and thus there is movement of electrons in a clockwise direction. So electrons move in a clockwise direction through the wire, through the external supply. And if you all remember again from 201, we take current direction as the opposite of the flow of electrons. So current is now flowing in a counterclockwise direction, which lines up with the passive reference configuration for a power supply. Current always goes from minus to plus. Everyone remember that? Passive reference configuration. Polarity of the voltage determines which direction the current is flowing. If you have 2 points in a circuit, both at the exact same potential, there is no mismatch, charges are equal, nothing flows. If one point is higher than the other, then the current flows from high to low, from plus to minus. Okay? Except when it's a source. When it's a source, it goes from minus to plus. Let's take a 10-second pause. Think over that. Let me know if you have any questions so far. Yes. Just a way to get charge moving. Question being asked is it just to get the electrons flowing? And the answer is yes. We connect an external supply. Until the external supply is connected, the electrons are just floating above the surface. Once you connect an external energy source, then the electrons are attracted. And thus they start moving. All right, any other questions? Okay, so this was about connecting the positive end to the anode. What if you reverse the connection? What would happen? If the negative of the power supply was connected to the anode, what would happen? No more charge attraction. Nothing would happen. Electrons would just flow towards the cathode. So there's no current flowing. So if you connect the supply here, then current flows. If you reverse the supply, no current flows. So it's a one-way switch, nonlinear device. And the name for this vacuum tube was a diode. Comes from the fact that Di stands for 2. And the ode, it's not ode to joy, it's an electrode. So 2 electrode device, diode. This was the earliest form of a vacuum tube. Then researchers inserted one more excuse me, one more electrode inside the vacuum or inside the tube. 3 electrodes, triode. Then you have 4 quadrode, pentode, hexode, and so on and so forth. There were vacuum tubes with like, I think 9 or 10 electrodes, probably even more than that. Okay, so the earliest electronic computers used vacuum tubes. The most famous one of them is known as an, let's see, ENIAC. US government gave a contract to, I believe, UPenn way back in the 1950s or 1960s. And they built this computer system that was probably as big as this entire room, comprised of about 18 to 20,000 vacuum tubes. If something didn't work, it would take them an entire day to just figure out which tubes were not working and get them replaced. Okay, so that's where the name comes from. Diode, triode, basically 2 electrodes, 3 electrodes. Okay, then there was the discovery of the solid state transistor in 1947. Now, when I say discovery, I mean an actual working device. People have been researching electronics for a long time, even before 1940s, but the first working transistor device was displayed in or was presented in 1947. And so we classify materials in 2 kinds: conductor and semiconductor. Well, actually, it's conductor, insulator, and semiconductor. And then semiconductor. Conductors are basically what we call wires in real life. Wires, cables, any wire or cable that you use, including our HDMI cables, USB cables, that's a conductor because it conducts electricity. And they're typically made out of some sort of metal that have a lot of free electrons available to conduct the passage of electrical energy. Semiconductors, however, only allow electron flow in one direction. So similar to the vacuum tube, in the vacuum tube, current can only flow in one direction. If you reverse the charge, current is not going to flow. So a solid state version, meaning there are no moving parts, hence known as solid state, is based on semiconductors. Semiconductor materials, the most common one, the most common one is silicon, right? Hence the name Silicon Valley. Again, conductor has a large number of free electrons. Semiconductors, they can function as an insulator or as a conductor depending on what we add to that material. Okay. So right here at the bottom of this table is our silicon. This table shows you the most common materials that we use in electrical circuits and their resistivities. Okay, resistivity. Resistivity is a material property. Resistivity is a material property noted by the Greek letter rho. That's what this is. This P looking character right here is the Greek letter rho, R-H-O. It is a material property. And material property is fixed. When I say fixed, okay, so this entire class, if I say something is fixed or it's a constant value, again, understand that we are talking about just room temperature. Okay, we are not talking about really hot or really cold environments. We're talking about room temperature, everyday normal use. So material property, it's a constant value at room temperature. As you can see, the resistivity for these materials, actually only up to here. Is in fractions. 10 raised to minus 6, 10 raised to minus 7, very, very low, meaning it hardly has any resistance at all. It does not have any resistance. Yes. So that's a good question. So the question being asked is, how does resistivity change with respect to temperature? Correct? So resistivity can change, can either increase or decrease with temperature. Materials that have, let me go a little bit of tangent. So if the resistivity, the resistivity of materials increases with increase in temperature, it is known as positive temperature coefficient material, PTC. Where rho increases with increasing temperature. And obviously it decreases with a decrease in temperature. And then you have negative temperature coefficient, where it decreases as temperature increases. Okay, there's applications in real life for both kinds of materials. Yes. Sorry, what? Not really. Not really. So the question being asked was whether PTC and NTC terms were relevant to the class. Well, it's knowledge, it's information. But if the question is that, if I'm going to test you on these, then the answer is no. Okay, so compare the resistivity of these conductors above with that of silicon. Insulators are a different class of materials where the resistivity is very, very high, meaning there are no free electrons to conduct electricity. Hence, they work as an insulator. They prevent. Silicon and germanium fall somewhere in the middle. They have resistivities that can allow them to function as an insulator or as a conductor. So let's take a 10-second pause. Think over that. Think over the material we've covered so far. Let me know if you have any questions. Yes. That makes sense. Yes. Silicon is a semiconductor. Yes, we'll talk about that in just a few. Yeah. With the device that would be not silicon as a material, but the device would be unidirectional. Yes. Any other questions from anyone? Okay. So what is it that would make silicon a semiconductor? Well, silicon and germanium, these atoms, have 4 electrons in its outermost orbit, or the valence orbit. Okay. And these 4 electrons, let's say it's one here, one here, one here, and one here. Okay, on four sides. In a stable crystalline silicon structure, each silicon atom is surrounded on all 4 sides with another silicon atom. They share these electrons among themselves, and they form what is known as a covalent bond. So once you have this covalent bond, they share the electrons and they have a stable outer orbit. So 4 electrons plus 4, 1 each from the 4 surrounding, would give them 8 electrons in their valence shell. And thus they have a stable structure. They have a stable crystalline structure. Okay, and that's what this diagram is showing. Each silicon atom is bound with 4 silicon atoms on all 4 sides, or 1 silicon atom on all 4 sides, thus having 8 electrons in its outermost orbit. Now, if you have a silicon structure and it loses an electron or it gains an electrons, what happens? You have an extra electron. Let's say it's coming from somewhere. You have an extra electron. Then you have 1 extra negative charge. If an electron moves out of its spot, the movement of an electron if it moves out of its spot, and electrons can do that, okay, it leaves behind an empty spot where it was originally bound to that atom. The atom now becomes a positively charged ion. But more importantly, the absence of an electron creates empty spot, and the spot is known as a hole. They couldn't find a better term. It literally is used as a hole. And hole is considered as a particle similar to electron with a positive charge. Okay. So again, I'll repeat this again. Electrons can move out of their spot, okay, depending, and this again goes into quantum mechanics and quantum physics. Electrons are in the outermost shell. Semiconductors, there is a gap known as the energy band gap between the valence shell and the conducting shell. If an electron acquires enough energy, it can jump into the conduction band and be able to move around in the structure. When it moves out of its spot, it leaves behind an empty spot. The technical term for that empty spot is a hole, H-O-L-E. And a hole is considered to be a particle similar to an electron, and it has positive charge. Because the electron took the negative charge with it, the positive or the protons are still bound in the nucleus. We are getting too much into semiconductor physics, but we'll move away from that in just a little bit. So that net effect of an electron moving out means there's an extra positive charge in there. So the hole is termed as having a positive charge. So we think in terms of electrons which have negative charge and holes with a positive charge. Okay. This is a very important concept to understand everything else. So let's take a pause. Let me know if you have any questions. We create a positively charged semiconductor. So the question being asked is, what is the benefits? Well, I would say in some cases, this is a naturally occurring phenomena. And you, of course, create these also. But when an electron moves out of its own volition, it creates a positive charge. So it just is. It is up to us humans to actually use it in any fashion we want. But the benefit of thinking about holes as a particle is that it makes analysis easier. Otherwise, you would think electron goes from here to here to here. So as shown in the diagram, you have an electron that moves out or away from this spot. When it moves out, this silicon has gained a positive charge. But it's not gained, it is inherent to the silicon atom itself. It's just that the electron moved away from it, taking the negative charge with it. So what it's left behind in the spot is an empty spot in a net positive charge. Now, to make analysis easier, researchers gave it a name, called it a hole, because every time an electron moves, let's say the electron is moving towards the right, what happens? The empty spot moves towards the left. And so it's useful for analysis to think of a hole as a particle itself with a positive charge that moves in the opposite direction as that of the electron. Yes.
So is there any way to change then you have a positively charged silicon to negatively charged, which just seems like a wire with extra step.
The question being asked is, can we change? Yes, depending on what impurity we mix with the silicon. That's coming up in the next few slides. So impurities would be something that is not intrinsic to the material. So if we add something, it's an impurity. So the intrinsic and extrinsic would mean, intrinsic means it's inherent. It is inside that system, right? If we talk about people, we say people have some intrinsic characteristic traits. So in terms of material, you have some intrinsic properties, and then you have some extrinsic properties because we add something to that material and the response of that material changes. So for semiconductors, there are a certain amount of electrons that are available for conduction. And those electrons are known as Ni, or the intrinsic concentration of these electrons, Ni. And I'll explain in brief why that is. You've heard of the Kelvin scale, named after Lord Kelvin. What is absolute zero? Well, in terms of value. In terms of value. 0 degrees C is about 273 Kelvin. Okay, 273 Kelvin. It's not degrees Kelvin, it's just Kelvin. I don't know, it's weird. I just learned to roll with it. So 273 Kelvin is basically 0 degrees C. Okay, 0 Kelvin is termed as absolute zero. Really, really cold. Really cold. We'd probably have to go to Neptune. Probably it's even colder than that over there. Anyway, the point I'm trying to make is at absolute zero, all the electrons in a semiconductor are bound to the atoms. They are fixed in position. The energy band gap is large. There are no electrons that can go cross over because there is no energy at all. As the temperature rises above absolute zero, meaning as you start going towards room temperature, the thermal energy that is available at room temperature, or even at 0 degrees C, is sufficient enough for the electrons to break free of some of their bonds. Some electrons, not all. And that's where these free electrons come from. It's from thermal energy. Remember the vacuum tube where you heat it up so much that you have electrons that acquire thermal energy and they're now free to float above the surface of the cathode. Okay, and so silicon and germanium are intrinsic semiconductors for that reason. They are known as intrinsic semiconductors because inherently at room temperature, they have a number of free electrons available for electric current conduction. For conductors like metals, they have a huge number of electrons that are available at room temperature, right? So if you have any sort of metal, copper, gold, silver, any metal has a huge number of electrons. There is no energy band gap in a conductor. They actually overlap. Okay, the electrons are just always available for conduction. So for silicon, Ni is 1.5 times 10 raised to 18 electrons for a space that is about 1 meter cube in size. Yes, Lee. The amount of electrons, it's just, well, it depends on what we compare it to. If you compare it to a conductor, that's low. If you compare it to an insulator, that's very, very high. So it's somewhere in the middle. That's why semiconductors. Yes. Yes, typically. So this value, question being asked was about, first question was about whether this value is high or low. And the answer would be, it depends on the perspective. And the second question being asked was whether this is valid at room temperature. And the answer is yes. And room temperature, of course, varies, but in general, it's considered to be about 20 or 25 degrees C. Depends on who is, who we ask. So here, here is the main point. If we take a conducting material and you add something to it, anytime we add something, we say it's an impurity. It does not belong in that material. It's not inherently available in nature, right? If you have a material and you add something to it, any sort of addition is an impurity. For a semiconductor, when you add impurities, depending on what kind of impurity we add, we can decrease its resistance, or we can also increase the resistance. But we don't care about that. We only care about decreasing the resistance and increasing the conductivity. When we increase the conductivity, resistivity and conductivity, by the way, are reciprocals of each other. They're opposites. So increases the conductivity, and we can create a conducting material from that semiconductor. So this is a very important concept. And why we call it a semiconductor? We add a impurity material and we create a conducting material. Let's take a 10-second pause. Think over those concepts. Let me know if you have any questions. Yes. You're talking about conductivity? Oh, question being asked is whether resistivity is the same as resistance? No. Let's see. Resistivity is a material property. Resistance is something we can create using resistivity. So if we have a material, let's say a wire, doesn't matter how long it is. A is the cross-sectional area, and the length, of course, is how long that wire is. Resistance is noted by R, and it's given by rho L over A. Resistivity times the length divided by the cross-sectional area. Every single wire that we use, every single conductor we use inherently has resistance, inductance, and capacitance. Okay, even a USB cable like this one or an HDMI cable that we use for our, for our televisions or computers, it has resistance, inductance, and capacitance inherently. Okay, but the value of these R, L, and C quantities does not arise to the level of interference, so we do not care about them. A USB cable, let's say it's a charging cable, 6 feet in length. You plug it into the USB charger and you connect the other end into your smartphone or your tablet or anything else. It will work. It has some resistance, but it does not rise to the level of interference that would interfere with its functioning as a charger or a charging cable. Anyway, coming back here. So semiconductors, we add impurities, we decrease the resistance, and we make it conduct electricity. So the way it works is like this. We have silicon atoms, right? Crystalline structure, everything is balanced out. There are no free electrons except for the ones that silicon has intrinsically. We add a material from either column 3 or column 5 of the periodic table. If it's column 3, it has 3 electrons in its valence shell, meaning the outermost orbit. If it's from column 5, it has 5 electrons in its outermost shell. And you can see where this is going, hopefully. Let's say you plug in arsenic inside the crystalline structure of the silicon. Okay, you have a piece of silicon material and you bombard it with arsenic atoms. What happens? Arsenic has 5, well, whether it's arsenic or phosphorus or any material from column 5, it has 5 electrons in the outermost shell. 4 of those electrons will form bonds with 4 silicon atoms on each side. Actually, let's use a different color. So here's one. What happened? Okay. So here's one on the left, 2, 3, and 4. 4 electrons from arsenic are used up to create covalent bonds. There is 1 extra electron left over. And that electron is free to move about in the silicon structure. So now we have created a material that has an excess of negative charge. It does not create an ion because remember, the arsenic atom already has the equal number of protons or positive charge to balance out those negative charges. So it does not create an ion. but the negative charge is extra coming from that electron. That electron is free to move about the structure. So let's take a pause, you think on that, and let me know if you have questions. That makes sense. So what happens if you insert a compound from column 3? Oh, answer is correct. 1 extra positive charge. Because, and I have an error on this slide, instead of arsenic, it should be boron or gallium. Boron or gallium. Boron is by far the most common one. So it's from column 3. It has 3 electrons in the outermost orbit. Those 3 will form a bond with 3 of the atoms. So right here, and right here. The 4th one, there is no bond right now, but this arsenic, again, the positive charge and the negative charge inside it is balanced out, right? The protons are equal to the number of electrons. So it's an absence of an electron, hence it results in a net positive charge inside the crystalline structure. So it is 1 extra hole from a column 3 compound. Results in 1 extra positive charge. Okay, 1 extra positive charge. And the way we do that is by semiconductor manufacturing. If you are interested in taking that class, we do teach it during the winter. It's BMed 434 and BMed 435. Students go in the clean room when we actually build. We take a silicon wafer and you actually build a diode and a transistor on that silicon wafer. It's available, that class is available to all students from the engineering school, even outside of the engineering school. Yes. Sure. So the question being asked is, how would the addition of a material increase conductivity or basically decrease resistivity? So that resistivity, or not resistivity, resistivity is a material property. That's not something you can change. We are changing the resistance or the conductance of the material. Okay. So again, we use resistivity to create a resistor, right? Or we can use conductivity to create a conductor. And so if we have 1 extra electron or 1 extra positive charge or 1 extra negative charge, these charges are free to move around in the structure. And the result of that is that the material behaves like a conductor. Because any time electrons flow in a circuit, we say that current is being, flowing in a circuit, energy is being transferred, hence conductor. It's a little, I wouldn't say hard, but it's difficult to get your head wrapped around in such a short period of time. It takes a while. It took me a long time as a student to just keep holes, the concept of holes on the side, and try to treat hole as a particle. Because invariably I would think if electron is moving this way towards the left, towards the right, how is it that the hole is moving towards the left? And it took me a long time to actually get my head wrapped around that. So it takes a while to get these concepts. Other questions? Okay. Let's see what what magic happens when we have both of them together. So if we add boron or column 3 compound, we get one extra positive charge. We call this as a P type material because it has excess of positive charge. It has an excess of positive charge. Okay. The material overall has an excess of positive charge. When we add arsenic or phosphorus, we have one extra negative charge. And so we have a N-type material. Okay, N-type material. So just by itself, a P and N-type material are of no use. I mean, we can find uses for those, but for the purposes of our class and our discussion, not much use by themselves. The magic happens when we bring both of them into close contact. This illustration, by the way, is neither the top view nor the side view. Okay, the actual fabrication of a silicon wafer, and I should have brought one with me. It's a flat surface, and it's called a wafer because it's a very thin slice of a silicon ingot. So it's a very flat surface, and looking at it from the top, the structure would be something like this. This is just for informational purposes. This is a small cross-sectional piece of a large silicon wafer. So this could be made up of pure silicon, or it could have some impurities in it. And then we would deposit extra material, let's say in a small piece of that silicon. And so the junction would be somewhere over here. This entire material is made out of silicon, and a small portion of that silicon is embedded, let's say either boron or phosphorus. Okay, either boron or phosphorus. Everything else is silicon. So this diagram right here, this illustration that you see here, is neither the top view or side view. Anyway, let's see what happens. You have a positively charged P-type material. You have a negatively charged N-type material. When we say P-type material, it has an excess of positive charge carrying carriers. So these are known as charge carriers. They carry charge to the material. So excess of positive charge, excess of negative charge. When we bring them in close contact, meaning they are right next to each other, the electrons from here go over there, and the holes from the right, H plus, go towards the right. And what happens? Well, they recombine. Recombination simply means an electron plugs back into an empty spot. Okay, there's a hole, right, in that structure. Hole is just a positive charge, but physically speaking, it's an empty spot. So an electron can move into that empty spot. That process is known as recombination, which eliminates a negative charge and a positive charge from that structure. Okay, I'll repeat again. Recombination is a process of an electron moving into an empty spot. Valence band, electron moves in. It gets rid of one negative charge and one positive charge. So the charges in that region are depleted. So a whole bunch of empty spots and a whole bunch of electrons move into those spots. Those charges are eliminated from the structure. So this region in the middle is devoid or depleted of charges. There are no positive charges or negative charges in that region. Hence, it is known as the depletion region. There's a lot more going on in there, but this is by far the simplest of explanations. Not simplest, but limited explanations. What actually happens also is that because of the drift of the charge carriers, there's an electric field that is established in this depletion region, and that electric field will oppose any further movement of charges. Okay, but the concept that you need to understand is that the depletion region is due to the recombination of electrons and empty holes, and it is devoid or completely devoid of charge carriers. And charge carriers are electrons and holes. Okay, electrons and holes. So let's take a pause. Think over these concepts. Let me know if you have any questions. Any questions from anyone? Yes. By applying an external energy source. So the question being asked is, can we manipulate, or how can we manipulate the depletion region? And the answer is with an external energy source, which we will see in the next. Well, actually, we have it right here. Any other questions? So this depletion region, which is devoid of charge carriers, is what provides the non-linear or one-way street for a PN junction diode. Okay, so this device is known as a PN junction, and because it functions similarly to a vacuum tube diode, that nomenclature carried over from vacuum tube electrodes. Even though this does not actually have an electrode, it is still known as a diode. That's where that name comes from vacuum tube diodes. So this is a solid state version of a vacuum tube diode. The reason it's called a solid state is because there are no moving, physically moving parts, unless at the atomic level. The symbol is shown right here. It's an arrowhead with a line at the tip of the arrow. And again, as I said, the names carried over. And so the positive end is noted as the anode. The negative end is noted as the cathode. And when I say negative, it means it's the N-type material, and anode is the P-type material. Okay. A real-life diode looks like this, which if you take the lab, you will be able to use these. It has a silver band. Actually, depending on the company that makes it, could be silver, could be gray, could be other colors, depending on the packaging. But the band indicates the cathode. And I don't know why, but the cathode is noted with a K. The band indicates the cathode. All right, questions? It's a lot of information to take in. What I would strongly suggest and recommend is you think over this material, review it, but do not get bogged down into the semiconductor physics of things. Okay. You are going to use these devices as discrete components to build a circuit, how a circuit is going to work. So while it's good to have an understanding of the solid state physics, it is not essential for your, for the entire rest of the class. Which, some professors might say is a disservice to students, but I always find that, there's a fine line between giving enough information for students to understand versus giving a ton of information and confusing everybody. Okay, any questions? So far, so good? Okay, so the depletion region, of course, creates a barrier for current flow. So we'll cover 2 more slides and then we'll end. The depletion region is right here. It requires an external amount of voltage to overcome the inherent electric field that is set up. Remember, I said the charge carriers cross over, electrons combine with the holes, and the depletion region is devoid of charge carriers, gives rise to an electric field. That electric field opposes any further movement of charge carriers, unless you provide external energy to force the electrons in the holes to cross over the depletion region. And that, again, is a material property. For silicon, if you apply a voltage approximately equal to 0.6 to 0.7 volts, that is enough energy to overcome the electric field and cross the barrier across that depletion region. So what happens? You have positive applied here to p-type material. So electrons would be attracted from the n-type material and cross over. Make sense? The electrons are attracted. And at the other end, you have negative. So it repels the electrons, but attracts the holes. So it pushes the electrons one way and attracts the holes the other way. And you have movement of charge carriers going across the junction. Your movement of charge carriers going across the junction, and thus current starts flowing. So if electrons are moving in a clockwise direction, holes are moving in the opposite direction. So these are electrons, and these are holes, which is also the direction of the current flow, which again ties back to the passive reference configuration. Current for a source always goes from minus to plus. Any questions? Okay. The process of applying an external voltage to this junction diode is known as biasing. So connecting an external source is also known as applying a bias, an external bias, right? It's known as biasing. And because we are applying positive to the p-type material, which allows current to flow in that one direction, it is known as forward bias. So if you connect, or if you bias the p-type material positive and n-type with negative, we state that the diode is now forward biased. The diode, the PN junction, is now forward biased. If you connect it the opposite way, we say it's reverse bias. P-type material connected to negative, and N-type material connected to positive. And I will expand on these on Wednesday because we are out of time. So we'll end class here today and we'll pick up here again on Wednesday. All right. If you have any questions, again, reach out to me anytime you want. Mondays and Fridays, I teach the lab associated with this course, which is right after at 12:10. And so would not be able to answer emails or answer questions until after the lab finishes, which is 3 o'clock. Wednesdays, again, right after class, I'm available. So again, think over all of this, review the material as soon as you can after class, and then let me know if you have any questions. Yeah.